Let's talk now about the Gateway Load Balancer. Gateway load balancers allow you to manage and deploy third-party virtual appliances, such as Networks Appliance in the AWS cloud. Third-party appliances are those published by vendors other than AWS. These appliances are typically used for network security and analysis functions, including firewalls, intrusion detection and prevention systems, and deep packet inspection systems. Before we dive a little deeper into gateway load balancers, let's first remember what it was like back in the days when cloud services were not so popular. Everything from the servers to the network appliance, such as firewalls or intrusion detection and prevention systems, used to be on premises and deployed as hardware in the corporate data center. When traffic came from the internet, it was intercepted by the network appliance and forwarded to the servers. Then, along came cloud services. Customers started moving their servers to the cloud while the network appliance was still on premises because it had not been virtualized or made available in the cloud. This meant that traffic had to flow through both environments. Therefore, when traffic came from the internet, it was inspected by the on-premises network appliance and then forwarded to the cloud servers over a VPN connection. Similarly, response traffic from the servers was forwarded to the local network appliance before being returned to the internet. As you can imagine, this configuration is complex from a routing point of view and also from a latency point of view. Then, network appliance vendors virtualized their products and made them available in the cloud. So now, incoming traffic is intercepted by the virtual network appliance, inspected and forwarded to servers in the cloud. While this simplifies routing, it still had a problem. The virtual network appliance is a single point of failure. To solve this, additional virtual network appliances were added, but load balancing between them was still a challenge. Load balancing had to be done manually with a routing configuration because there was no load balancer that would do it automatically. Of course, this was solved by the Gateway Load Balancer, which now allows load balancing of incoming traffic between several virtual network appliances. So now, the incoming traffic is intercepted by the Gateway Load Balancer, which forwards it to the registered virtual network appliance. These inspect the traffic and forward it to the application servers. Similarly, when the servers respond, the virtual network appliance receives and inspects it, forwards it to the Gateway Load Balancer, and finally forwards it to the requesting client. This is how the Gateway Load Balancer works. So, let's talk about some of the features of the Gateway Load Balancer before implementing it. The Gateway Load Balancer is transparent. This means that the source and destination do not know that there is a load balancer in the path. The Gateway Load Balancer distributes traffic and also scales its virtual network devices. It operates at Layer 3, also known as the network layer of the OSI model. The OSI model, as I discussed earlier, is simply a conceptual framework that divides network communication into different layers. Layer 3 is the network layer. Since the Gateway Load Balancer operates at the network layer, it forwards all IP packets through all ports. Port numbers, protocols, and applications are functions of the higher layers. Being at Layer 3 or network layer, the Gateway Load Balancer does not distinguish traffic on these components. It simply forwards all IP packets. Now, we have seen in previous classes that ALB and NLB require a listening agent configuration to match incoming traffic. The listening agent configuration has protocol and port information. The Gateway Load Balancer, on the other hand, will simply forward all traffic it receives to the registered devices. The Gateway Load Balancer supports health checks, which ensures that traffic is forwarded only to healthy targets. Unhealthy targets are removed from the log. Traffic between the Gateway Load Balancer and its registered targets is exchanged using the Geneve Protocol. The Geneve Protocol, Generic Network Virtualization Encapsulation, encapsulates IP traffic with a header. Encapsulation is the process of adding a wrapper around the packet. Encapsulation ensures that the original packet remains intact. This means that when the virtual appliance receives the packet from the Gateway Load Balancer, It is exactly the same as the one sent by the client. This is because the original packet is encapsulated. That is, a wrapper is added to it to ensure that it remains intact. The Geneva protocol uses UDP port 6081 as the destination. Therefore, this port and protocol combination must be added in the security group associated with the virtual appliance. Let's see how this works visually. Here we have an application server associated with a gateway load balancer. The gateway load balancer has a virtual network appliance registered to it. The virtual network appliance will inspect the incoming traffic to the application server. Suppose an internet user needs to access the application server. To allow inspection by the virtual network appliance, the traffic must first reach the gateway load balancer and not the application server directly. This can be achieved with a routing configuration. We will configure it in the next classes. So, the routing configuration makes the request packet arrive first at the gateway load balancer. It encapsulates the packet, that is, adds a wrapper, and forwards it to the virtual network appliance using the Geneva protocol on UDP port 6081. The virtual network appliance decapsulates the package, that is, removes the wrapper, and sees the packet as it was sent by the user, which, as you can imagine, is crucial for inspection. The virtual network appliance then re-encapsulates the packet and forwards it to the gateway load balancer. The gateway load balancer decapsulates the packet and forwards it to the application server, which is the actual destination. Note that we are still dealing with the original request packet. Similarly, when the server responds, the packet is intercepted by the gateway load balancer, which encapsulates it and forwards it to the virtual network appliance. The virtual network appliance decapsulates and inspects it. After inspection, it encapsulates it again and sends it to the gateway load balancer. The gateway load balancer decapsulates it and forwards it to the requesting user. Now, you may be wondering, if the gateway load balancer is transparent in the network, how can it intercept the packet? Well, the gateway load balancer does not provide a DNS name like other load balancers that your clients can access, such as the ones we have seen before. Instead, we use routing tables to tell AWS how traffic should be routed, causing it to pass through the gateway load balancer. But if the gateway load balancer is transparent and does not provide a DNS name, how do we route traffic to it? To do this, we use an endpoint, a gateway load balancer endpoint. The endpoint can be used to direct traffic to it. An endpoint is a network component that enables communication between AWS services. Any traffic directed to the endpoint will be received by the gateway load balancer, which will forward it to the registered appliances. This will all become clear in the next class when we look at the configuration scenario. For now, just remember that gateway load balancers are used for load balancing between virtual network devices that are typically used for security, monitoring, and network inspection purposes. So, with this in mind, let's look at the configuration scenario we are going to deploy.